right. Let's get going. So, right, again, this semester we're starting talking about kinetics first, and then we'll go into the wonderful world of quantum mechanics after that. Okay. So, today and then kind of potentially tomorrow, we'll talk kind of about integrated rate laws and some things of that nature. And then after that, we're basically the rest of our time in kinetics is talking about reaction mechanisms and how do we solve for rate laws for reaction mechanisms and doing many different examples for reaction mechanisms. So I have a lot of wonderful time doing that. Okay? So today, thinking about first order reactions, integrated rate laws, and half-life. Okay? So right today, we're going to be kind of reviewing again the first order rate equation, the integrated rate law, the half-life of first order reactions, kind of understanding some of that stuff. Okay. Right. As a reminder, right. Hopefully, this is stuff you've kind of seen before. Okay. The lecture slides online, which hopefully people have watched. Right. Goes through the derivation of this integrated rate law, ln of a equals minus kt plus ln of a naught, or a equals a naught times e to the minus kt, okay? Where a naught is your initial concentration of reactant A, right? A is the current concentration, T is time, and then Kr is here your rate constant, okay? Now this is Kr here versus Kr prime, and that's just because of the fact that there's this 1 over stoichiometric coefficient that appears kind of in this differential equation that you just lump in with the rate constant to kind of get this general expression, okay? All right. If the stoichiometric coefficient for your reactant A is equal to 1, right, then Kr prime is the exact same thing, okay? But if it's not, then that will affect this, right? Because if you think, right, if I have some rate of reaction, right, that has some rate constant associated to it, okay, and I'm looking at, say, what is the concentration as a function of time, right? If my reactant has a stoichiometric coefficient of 5, right, that decay of that reactant should be very, very quick, right? And so I should have 5 times the rate constant here. If A is 5, you'll get 5 times the actual rate constant of your reaction. And that will be kind of what is in up here, right? Which will give you a much faster decay than if your stoichiometric coefficient was, say, equal to 1. Okay? So what that stoichiometric coefficient does impact how quickly these things decay. Is again, they should, right? If you think about it just logically, right? The larger your stoichiometric coefficient, the quicker that concentration changes as a function of time. Question?
Concentration of A sub 0 is concentration of A is equal to concentration of A sub 0?
Say that again?
Is it concentration of A is equal to concentration of A sub 0?
Yeah. Oh shoot, yeah. Thank you. Yeah, the sub zero. Yeah, and I guess on the first one I put it inside. Yeah, I don't know. I guess I forget what's common to put it inside or outside. One thing I typed up a while ago. The other thing I typed up last night quickly. So I was kind of finalizing these slides and didn't pay attention to the fact that I used different notation for both of them. Yeah, but both those things mean this initial concentration. A naught, A sub 0 in the brackets, or A in the brackets sub 0 outside. I think the more common way to do it is the second way here. A concentration of A, then the 0 outside indicating the initial concentration. But I think I didn't do that here because I had this natural log function and I was thinking, oh, it's kind of the parentheses natural log. Anyways, that's irrelevant. But yeah, both those things mean the initial concentration. Right, and again, hopefully this integrated rate law is familiar to what you've seen in general chemistry, for those who remember, right, general chemistry, right, and the fact that that equation ln of A equals minus kt plus ln of A naught, right, is a linear equation, right? If you plot the natural log of A versus time, you will get a straight line, right, with some slope k, right? Or minus k is the slope, right? And then the y-intercept is ln of a naught, right? Okay. Right, and again, as I mentioned, right, if you have a larger rate constant K, or if your stoichiometric coefficient is large for the reactant, right, you'll get a much faster decay, right? So for the larger K, right, the decay of your reactant goes much more rapidly compared to the smaller value of K. Right. Question?
I haven't watched the derivation, but on the last slide, where does the -1 over A go? I know it'll be like the
Yeah, so you multiply the negative, you multiply both sides by negative A. You have dA dt equals minus A kr prime A. And then I call kr just A times kr prime, because they're both just constants. And so that's where the A goes, is it just gets lumped in with kr prime to get kr. And then the minus sign is just still there in front of like the minus K. Right. But yeah, so you multiply the minus sign on the other side. And then you have an integral of like dx over x and an integral of dt or whatever, you know, dA over A. So the integral of dA over A is ln of A, and then the other one just gives you t. So, yeah, so kr here is A times kr prime. I do it like this just to show that the stoichiometric coefficient does matter, right? In general chemistry, often they just do examples of stoichiometric coefficient 1, so it never appears, doesn't matter, right? But that stoichiometric coefficient does matter. It would appear in this final expression, okay? Right? I just defined this kr being A equal A times kr prime, just to give these equations in a familiar form. Right, this is the form that you typically have seen in general chemistry or other types of chemistry, right, where the stoichiometric coefficients don't appear, okay, but the stoichiometric coefficient does matter, right, and it could be, right, that this could be the rate of decay for two different reactants, okay, right, and it's just that one reactant has a stoichiometric coefficient of 1, and the other one has, say, a stoichiometric coefficient of 2, and then you'd have a faster decay for the reactant with a stoichiometric coefficient of 2 than that for 1. So the stoichiometric coefficients do matter in these integrated rate laws. Any questions about that? Just double checking that. Chat here. Okay, right. So let's do an example here. So I have some first order reaction. Okay, A going to P. I know 2/3 of the reactant remains after 28.5 seconds. What is the rate constant for this reaction? Take a minute for you guys to work on this, and we'll talk about it together. All right. Right, so this problem, we're told, right, how much of our reactants remain after a certain amount of time. So if I'm looking at what is, if I'm looking at anything that's relating concentration and time together, that means I should be using some type of integrated rate law. Okay. If I ever see a problem that has situations where I'm looking at concentrations and I'm looking at time, that's an integrated rate law problem. Okay. Doesn't matter what else is given in that problem, it's an integrated rate law problem. Okay. So looking at concentration versus time information, right? And so I use my integrated rate law. It's a first order reaction. So I use that first order integrated rate law here. I picked this one in the slide, right? You could have taken the natural log of this equation, started there, but that's fine, right? And again, at 28.5 seconds, your concentration is 2/3 that of the initial value, okay? So I can plug in for A, 2/3 A naught, and then plug in for T, 28.5, okay? The A naughts cancel, and you're just left with this equation here, 2/3 equals E to the minus 28.5 KR. Okay, taking the natural log of both sides and then dividing over that negative 28.5, and you get that the rate constant is 0.0142. The units for that is going to be inverse seconds. Okay, right, units for the rate constant has to be inverse seconds because it is a first order reaction. Okay. Yep.
For A naught, can we assume that it'll always be 1 since you're always starting with 100% of reactants? So 1, the log of, or ln of 1 is 0, so can we, like...
Yeah, so if you want to assume A naught is 0 for this, that's fine. If the initial concentration is equal to 1, that's fine. You can assume whatever initial concentration you want, and you'll get the same answer every single time. So yeah, so you can definitely do that, especially for first order reactions. You can assume some type of initial concentration, even if one's not given, right? And really, it's only first order reactions you can do that. First order reactions, you can answer a lot of the questions without knowing what is the total amount, just the percentage change. But if you know the percentage change for second order reaction, you don't have enough information to typically solve the problem. You need to know the total amount as well. So this is mainly only true for first order reactions that this holds. Okay. Other questions? Oh, there are some questions in chat. My apologies. I got that saying okay. Everyone's just saying what they got. All right, fantastic. So any other questions? All right. Right, and so in general chemistry, right, this is typically what you're focused on when you see this integrated first laws, right? Integrated rate laws, say for first order reactions, right, is say I measure concentration in the lab as a function of time. What should I plot in order to determine whether or not this is a first order reaction? And then how would I get the rate constant from that plot? So if you measure concentration as a function of time, what type of plot would you want to make in order to say, oh yeah, this is for sure first order or not? Yep. You want to plot the natural log of your concentration versus time, because that will give you a straight line, right? As scientists, we try to do any type of plot that gives us a straight line, because it's very easy to see a straight line, to know that's definitely a straight line, to fit to a straight line, right? Straight lines are great, okay? So we'll use whatever axes we need to get a straight line, right? And natural log of concentration versus time, right? Talk about the radius equation, right? You plot the natural log of your rate constant versus 1 over temperature, okay, right? We talked about some things in thermal chemistry related with plotting like 1 over temperature versus delta H or delta G or something like that, or equilibrium constant and stuff, right? So there's all sorts of different plots that we will try to make using whatever units, whatever kind of coordinates we need to for the X and Y coordinates in order to get straight lines, Because again, fitting to a straight line is very easy. Eyeballing a straight line, right? I mean, think about, right, when a lot of this stuff was done, you didn't have Excel or things like that, Matplotlib or whatever other programs you want to use to fit curves and things like that, right? So a lot of times you're doing this by hand, right? And so, you know, it's a lot easier to get the slope from a straight line and to tell if a line is straight, right, than it is to tell if a line is a parabola, right? Or to tell if it's x cubed or something else like that, right? So, so we want to plot natural log of a versus time. Here I say the natural log of a divided by a naught. You don't have to divide by the initial concentration, right? It's mainly natural log of that concentration versus time will give you a straight line, okay? Right? And the slope then gives you the rate constant, right? Negative of the slope is going to give you equal the rate constant, right? Because the plot here, right, y equals mx, right? And so m, here's your slope, which is negative k, right? So negative of the slope gives you the rate constant. Hopefully this rings some bells for some people about general chemistry, right? So let's say I was given this data, right, and I wanted to know, is this first order or not? Okay. So what would I need to do with this data to determine whether or not this reaction is actually first order?
You have to plot it versus the function of the natural log of pressure versus time.
Yeah, so I want to take the natural log of that data, right, and plot it versus time. Now here I took the pressure, right, I took the pressure and divided by the initial pressure, so I divided everything here by 10.9, right? So I did 10.9 divided by 10.9, 7.63 divided by 10.9, so on and so forth, right? I do that, and then the natural log of 1 is equal to 0, right? And so I have 0, 0 here, right? And then I get these negative numbers based off the natural log of the ratios from above, right? Right, and so then I have that data, right, where I take the natural log of my pressures, okay? And then again, in lab, you'd say plot that, fit it with Excel or something like that, right? If you wanted to know whether or not it was a straight line and you didn't have access to some computer or a calculator that could make this plot for you, right? You could just look at the slope between different points, right? So if I look at the slope from, say, time 0 to time 1,000, right? Okay, it's going to be the difference in the y-axis, you know, 0 minus negative 0.357 divided by 0 minus 1,000, okay? I did that in the opposite order here. I did, you know, negative 0.37 minus 0 and 1,000 minus 0, but whatever, right? And you get some slope here, okay? Do the same thing from, say, 1,000 to 2,000 seconds, 2,000 to 3,000 seconds, okay? You get plot, you know, take those differences, find the slope, okay? And you get the same number, basically, right? I mean, to whatever rounding, right? 0.00036, okay? So that slope is constant, right? A constant slope means you have a straight line, okay? Right, that is the definition of a straight line, is that it has a constant slope, okay? Any other curve that does not have a constant slope, right? Right? If you don't have a constant slope, it's not a straight line. If it's constant slope, it's a straight line, right? That you know, so it's very easy to tell if something is straight line or not. It's a lot more difficult to tell if it is x squared or x cubed or sine of x or whatever other things, right? But I can easily tell if it's a straight line by just looking at whether or not the slope is constant, okay? And it's constant, so that tells me that the rate constant for this reaction is 3.6 times 10 to the minus 4. Units for that should be inverse seconds. Okay, I didn't put it, but it should be inverse seconds for arguments. Questions about this guy? Yep.
When you got the P over P naught, is that just like to set the y-intercept to 0?
Yeah.
Or is it, okay.
Yeah, there's no reason to, you have to do that. I just did it just to, I mean, I did it mainly so then I had to plug in one less natural log because I know the natural log of 1 is equal to 0. So that is literally the only reason I did that. But I mean, I don't know if it's easier, simpler, or better, but it's just what I did. Yeah, you don't need to do that. You could just do the natural log of P, take the natural log of the numbers that were given, and not take this ratio, and you'll get the same answer. So, in terms of the slope, at least, right? Other questions? All right, another way to look at first order reactions is looking at their half-life, okay? The half-life, as a reminder to those who may have forgotten about it, is the time it takes for the concentration of your reactant to be reduced by its initial value, or reduced by a half of its initial value, right? Thus half-life, right? Not just a video game, but actual scientific thing, right? Half-life, right, is, again, as it's called, right? The lifetime it takes, or not lifetime, right? The amount of time it takes to reduce your concentration by a half, okay? So for first order reaction, I can just solve for the half-life by taking my integrated rate law, saying my concentration is a half of the initial value, that whatever time it takes is that T1 half, and I can solve for T1 half. When you do so, you get this final expression here, that T1 half is just equal to the natural log of 2 divided by KR. Okay. Now note here that this half-life depends only on the rate constant and not on your initial concentration. Okay, that is only true for first order reactions. Is not true for 0th order, 2nd order, any other order reaction. Only first order reactions is the half-life independent of concentration. Okay. Well, and that is very convenient because that is what allows us to do things like carbon dating, right? In carbon dating, I don't need to know what is the total amount of, carbon-14 I originally had. I just need to know what percentage had decayed. And I can get that by looking at ratio between carbon-14 and the nitrogen that it decays into. Okay. And I can just do that from taking a small sample of my object, right? I don't have to try to evaluate the total amount of carbon in my object, right? On a carbon date a bone, I don't have to, completely destroy the entire bone to determine the total amount of carbon in there and things like that, right? I can just take a small sample, assuming it's kind of a homogeneous mixture of things, right? And from that small sample, determine the percent of carbon-14 versus the percent that had decayed by looking at, again, the amount of the decay product, right? And that allows me to do carbon dating, okay? Right, and so, and again, that is very useful about the fact that it is independent of the concentration. Okay. Questions about half-life definition? Yeah.
I'm not seeing the bottom two lines, like how you get from the second down to the blue.
Yeah, so so for this line, what I did is I divided both sides by A naught, and that will give me 1/2 equals e to the minus kr t1 half. And then if I take the natural log of both sides of that, I get the natural log of 1/2, and then the natural log of e to the minus kr t1 half is just negative kr t1 half. And then the natural log of 1/2 is equal to negative the natural log of 2.
Okay, now I get it. Okay.
Yeah, so that's where that minus sign goes. If you can pull a minus sign in or out of the natural log if you take the reciprocal of whatever's inside that natural log. Yeah, so that's where the minus sign goes, and that's why 1/2 becomes 2. Okay. Any other questions? All right. So what would be the half-life of this reaction? Roughly speaking, 0 seconds, 50 seconds, 100 seconds, 200 seconds, or none of these, right? Like if you think it's like 105, just say 100 seconds, right? My answer to this question is not going to be, oh, it's 103. So it's none of these suckers, you know what I mean? Like you round it roughly if you feel like it's one of those, right? So if you feel like it's 300 seconds, okay, then, you know, put none of these. So what do people think? Yeah, C, right? A lot of people saying C online and C in class, right? And that's true, right? Half my initial concentration is 1, half of that is 0.5, right? Get to half of that concentration, I'm basically at 100 seconds. Okay. All right, so C here, 100 seconds is the half-life of that reaction. Okay. I don't know why I have this question here. This is literally the exact same question with the exact same data, right? Again, here it's looking at the concentration versus time and asking what is the half-life. Okay. Again, you just look at when do I get to half my initial concentration? How long did it take? 100 seconds, right? I guess here B is the answer instead of C in the previous one, but still 100 seconds. Exact same data. Should have really changed up that data. All right. So let's say I have a radioactive isotope that decays to 60% of its initial concentration in 3,025 years. I know this is a first order decay. The question is, what is the half-life of this isotope? So it's going to be sometime longer, exactly the same, or something shorter, right? And yeah, see here, right? So, right, it took 3,025 years to get to 60% of its initial amount, which is not quite 50%, so it's not yet reached the half-life. So yeah, so C, sometime longer than 3,025 years. Yep. Right. If you're actually trying to calculate that value, right? So we could actually calculate what the half-life is. So let's see here, 60%, 302. Right. So if we actually want to calculate that value, right. So I decay 60% the original amount, right? Which is basically saying my concentration of A is equal to 0.6 times A naught. Okay. And this is the time that it took. Okay. So that's saying that 0.6 A naught equals A naught times e to the minus k 3025. Okay. So those cancel, right? So get the natural log of 0.6 equals negative k times 3025, right? Divide that over, I get negative ln of 0.6 divided by 3025 equals k, right? And then the half-life for first order reaction is just defined as the natural log of 2 divided by k. Okay. Yeah. I'm going to change this. I'm going to write 10 over 6 divided by 3025. Okay, so it's T1 half 2 divided by ln 10 over 6 times 3025. Okay. Whatever that number ends up coming out to be. How I got this 10 over 6 thing is I use the fact that 0.6 is equal to 6 over 10, right? And so I did the natural log of 6 over 10 minus is equal to ln of 10 over 6. Yeah. Just to let you know how the heck I went from negative ln of 0.6 to positive ln of 10 over 6. right? But so that's how I'd solve for the actual half-life. Okay. Again, you end up getting a number that's greater than 3025. Questions about this? All right. So here, a little bit more of an involved question. So here I have the decomposition of acetic acid at 1189 Kelvin as proceeds by two parallel first order reactions. Saying that they're parallel first order reactions means that they take place simultaneously and don't affect each other whatsoever, right? That basically that acetic acid is decaying to those two different products, right? That one molecule is decaying to the first product, another molecule happens to decay at the second product, right, during the same time. Okay. Now they both have different rate constants. Okay, K1 is 5 inverse seconds, K2 is 8 inverse seconds. The question is what is the maximum percentage yield of the ketene, okay, which is the product in the second reaction, the CH2CO, right, obtained at this temperature. Okay. So we're going to do this example now, but this type of question and talking about these percentage yields and things like that will pop up again when talking about photochemistry. Photochemistry is all about parallel first order reactions, okay, and getting lifetimes of excited states, percent yields of types of emissions, types of decays, and all this other stuff is all just related with kind of parallel first order reactions. And we'll go through kind of things in more detail here, but we'll see a very simple solution to this problem in the end. Okay. Take a minute, think about how one might try to solve this. So before, I'll give you a little bit more time, potentially kind of work on this, thinking it, but I first want to just ask this question as a way to kind of get people started potentially, right? What is the percent yield of CH2CO? How would you find the percent yield of some product in a reaction? How would you do that in the lab? What would you do to get the percent yield for some reaction? Yeah, right. So in lab, right, we think of actual over kind of the theoretical yield, okay, right? So right, and so that's yeah, and so we have something similar to that here, right? Now here we're doing all things kind of, we're asking what is the maximum percent theoretical yield, right? Again, because here I have multiple reactions, and so, right, yeah. How do I think about it? right? So again, that percent yield, right, as you talked about in the lab, we often do it as actual over theoretical, right? Right, so we can, it's a similar type of thing here, right? It's what is the actual yield of concentration of CH2CO, right? What is the actual concentration of the thing I want, okay? What's that final concentration? Right, I'll put like a final here. What is my final concentration after the reaction is completed, right, of CH2CO compared to my percentage, right? How would you get your theoretical yield, right? Yeah, you look at your reactant, right, and look at how much concentration of my reactant do I have, and then assume that goes all the way to just this one product, right? And so it's the same thing here, right? It's that concentration of, shoot, what's my reactant? CH3COOH, is that it? Yeah, fantastic. Okay. All right, and that's, say, the initial concentration of CH3COH, right? And then you'd multiply by 100 if you want to get like a percentage, right? Okay. But given some initial concentration of acetic acid, right, what percent of that acetic acid decays into CH2CO, right? That's what we're asking for, right, in terms of that percent yield. And so the question is really, right, what is concentration of CH2CO equal to, right? That's what we're curious about. Okay. Because if I know that, and if I can solve for that in terms of my initial concentration of the acetic acid, right, then I'm going to just plug that back into this equation here and solve for my percent yield. So I'm going to go back to the slide real quick, and I'm going to write down some of these equations. Right, but kind of think about how you might try to solve for that concentration. As a function of time. So what is the change, right? So if I want to get the concentration of CH2CO over time as a function of time, right? I can't necessarily get that straight away, but I can get that related to the fact that I know that, say, the change in concentration of CH2CO as a function of time, right, is just equal to, right, the rate of this reaction, which we know it's a first order reaction. So that rate of that first order reaction is just the rate constant K2 times concentration of CH3COOH. Right? So I know this is true, and I know this to be true because, again, let me just, right? Because I'm asking, what is the change in concentration of CH2CO as a function of time? Well, that is just equal to whatever the rate of this reaction is, right? It's just equal to the rate of reaction 2, okay? Well, again, we're told these are first order reactions. So the rate of reaction 2, right, is just the first order rate law, which is just K2 times CH3COOH, right? So that's how I get this equation, right? Now I have some variable x here, CH2CO, which is x. I got another variable t here. And then I got something else, CH3COOH, at, say, y, right? So I can't just integrate this out or something like that, get some simple thing, okay? I need to know what is, right? To solve for this, I need to know how does CH3COOH, right, change with time, right? How is this a function of time, right? What is the change in CH3COOH as a function of time? Because then I can plug that into here, right? And if this is just something as a function of time, then I can integrate this equation to solve for my concentration of C2CO, okay, as a function of time, right? So then the question is, right, let's get that change, or that concentration of CH3COOH as a function of time, it's dt, right? Now, I'll try to zoom out here just a little bit so you can still see most of this stuff, right? So as I did kind of from here before, right, this rate of change of CH3COOH, right, as a function of time is just, right, minus, I'll say V1 minus V2, right? It's the rate of reaction 1 minus the rate of reaction 2, okay? And again, we know that because, right, the rate of change of a reactant is related to the rate law, or the rate of the reaction, based off of the stoichiometric coefficient, right, which is just 1 in this reaction, okay? So the rate of change of CH3COH dt is equal to just minus the rate of that reaction for both reactions, okay? So the total rate of change of CH3COH is just sum of these two things, right? Which plugging in is just equal to minus K minus K1 plus K2 times concentration of CH3COOH. Okay, right? Because V1, its rate law is just K1 times CH3COH. V2's rate law is just K2 times concentration of CH3COH. So I just pull the CH3COOH out from there to get minus K1 plus K2 times concentration of CH3COOH. Questions about this, about how I got to where I got to so far before we move on, okay? Because some of these steps are similar types of steps you'll take when we start talking more and more about reaction mechanisms and solving for rate laws and reaction mechanisms. You'll often do something like what I did here and here, okay, in these two spots, right, where you will say, okay, the rate of change of concentration of some reactant or some product is equal to what rates of reactions, and then what are those rates of reactions equal to in terms of rate laws, okay, to get these types of differential equations. Okay? These are the type of differential equations that we will be trying to solve for and write out when we discuss reaction mechanisms and getting rate laws from those things. Okay? So please, if you have questions about how I got where I got to with any of this, please ask. Right, and so this reaction, this equation here, right, this part, okay, this is just the same thing as dA dt equals minus KRA, right? This is just what this, right, if I call CH3COH A, and then K1 plus K2 is KR, right, I have this differential equation, which we solved for before, right? This is just our differential equation for first order reaction, right? So this says an integrated first law, okay, concentration of A equals concentration of A naught, e to the minus KRT, right? And so just, right, using the fact that I'm calling A CH3COH, right, and then KR is K1 plus K2, okay, I get that the concentration of CH3COOH as a function of time is just equal to the initial concentration of CH3COOH times e to the minus K1 plus K2 times time. Okay. Right, so notice here, right, that the integrated rate law for some set of parallel first order reactions is just the same as any other integrated rate law for first order reaction. It's just the rate constant is the sum of the rate constants for all the parallel reactions. Okay. And I'll just, tell you now, in general, if I had 6 parallel first order reactions, okay, I would get this exact same integrated rate law. It would just be K1 plus K2 plus K3 plus K4 plus K5 plus K6. Okay. And again, this is going to pop up again when we get to photochemistry, right? Okay. So now that I have that, I can finally solve this equation up here, right? By plugging in for what CH3COH is in terms of time. Okay. So I get dCH2CO dt equals K2 times concentration of CH3COOH, not the initial concentration, right? E to minus K1 plus K2 times time. Okay. I'm going to rewrite that equation, or I'll just do this. So again, I got this equation here, the change of concentration of CH2CO as a function of time, right? By just plugging in for the concentration of CH3COOH in terms of stuff related to time. Okay? So then if you notice here, right, this is dCH2CO equals K2 CH3COOH naught times e to the minus K1 plus K2 T dt. Okay. Right? And so this equation is just a differential equation that I can integrate both sides from sometimes 0 to t. My initial concentration of my product here, CH2COH, is 0, right? And then at some time t later, I have my final concentration of CH2CO. Okay. Right, and so the integral of the left-hand side just gives me concentration of CH2CO. Okay. The right-hand side, okay, these two things are constants, K2 CH3COH, so that just gets pulled out, K2 concentration of CH3COOH. Oops. Right? Okay, and so I'm just looking at what is the integral of e to the minus, kt dt, right? What's the integral of e to the minus x? Yeah, right. Or if in general I want to say, right, what is the integral of e to the minus ax dx minus 1 over a e to the minus ax, right? Then if I'm integrating this from like 0 to 10, right, I'd evaluate that at 0 to 10, right? And so, right, this integral here is just minus 1 over K1 plus K2 times e to the minus K1 plus K2 dt, sorry. T. And then I have to evaluate that time t equals 0 and time t equals t, right? So I'm going to pull out this in front, right? So again, I have my concentration of CH2CO equals K2 over K1 plus K2 times the initial concentration of CH3COOH. Okay. Okay. There's this minus sign here. Okay. What I want to do is I'm going to write, normally you do time t minus time 0. Here I'm going to do time 0 minus time t because of this minus sign here. So at time 0, this is just equal to 1. Okay. Because plug t equals 0 into here, that's 0. E to the minus 0 is just equal to 1. So this is 1 minus e to the minus k1 plus k2 t. Okay. All right. So that is my final expression for what is the concentration of my ketene as a function of time. Okay. And so, right, going way back, and I'll put that back up. Right, going way back to the beginning, right, in my percent yield, right, I'm wanting to know what is that final concentration of CH2CO, right? And so how would I get sort of what the final concentration would be from this, right? What would I want to do? With the final concentration, right?
Like for the ketene,
Yeah, for the ketene.
I mean, wouldn't you have to know the initial concentration and time of the final concentration?
Yeah, so right, that final concentration, right, we're talking about like theoretical yields, right? So what is the, like, how in theory, how would I get the final concentration, right? Again, assuming whatever initial concentration. Sorry, I forgot to put the little knot here, right? That's an initial concentration, okay, right? But again, in theory, right, what would I do in lab to make sure I'm at the final concentration of my products? What would you do? Would you end the reaction after 5 minutes?
Time goes into like let it go.
Yeah, you just let it keep going and going and going, right? So our final yield, our theoretical maximum final yield for our ketene, right? Right, is just when time goes to infinity, right? I let this thing go to completion. I let it, I wait forever for this to make sure it's completely reacted, right? So as time goes to infinity, this is going to be e to the minus infinity, right? E to some very extremely large negative number is just equal to 0. Okay, so as t goes to infinity, my final concentration of CH2CO is going to go, so final, okay, is just going to be K2 over K1 plus K2 times the initial concentration of our acetic acid, CH3COOH. And then this is going to be 1 minus 0, which just gives us 1. And so this is our final concentration. So finally, plugging this back into our initial thing, right? Our percent yield of CH2CO, okay, is just going to be equal to K2 over K1 plus K2 times CH3COOH not divided by CH3COOH not, okay, which these two things cancel, right? And so this percent yield is just equal to K2 over K1 plus K2, okay, which happens to be 8 over 8 plus 5, or 8 over 13. Okay? And I guess times by 100, right? Times 100, right? Times 100. If I want to get a percentage, right? So that's our final percent yield, 8 over 13. Questions?
If you were trying to
Yeah, so if I wanted to know what was the percent yield for one of the products in the first reaction, yeah, the percent yield would just be K1 divided by K1 plus K2 times 100. So again, this is for like parallel first order reactions have this general thing, right? The percent yield, right, of some product, right, is equal to the rate constant for that product divided by the sum over all the other, over all rate constants for all the first order competing reactions. Okay. And like the total lifetime of your acetic acid is going to be related with 1 divided by the sum of rate constants. Oh, sorry. And things like that. And so, yeah, so this, let me see if I have kind of this on a slide here. All right. So I go through all this stuff on the slides as well, which is, been posted. And that number gives you 62%. Oh, okay, no, I don't have it. Let's open ahead something, right? But again, in general, okay, we'll see this again pop up in photochemistry. But when you have these competing first order reactions, the percent yield of this thing you care about is just what is the rate constant for that process you care about divided by the sum of all possible rate constants, right? It's sort of like probability, right? What is the outcome you care about, the number of times the outcome you care about happens, divided by the total number of outcomes, right? It's the same type of kind of idea here, right? What is the percentage, right? What is the time it takes to get the product you care about versus divided by the time it takes to get all the products sorted. Again, we're not talking about times, we're talking about rate constants, but yeah. Question?
Third line from the bottom, that was just relating back to the, just the, I can't use words right now, to just the basic formula that we started with in the beginning of the problem.
Yeah.
We were just talking about stuff. You just came back and just threw that in.
Plugged in what we saw for.
Okay.
Yep. Mm-hmm.
All right. It
Yeah.
just kind of came out of the mire, so I was just wondering.
Yeah, right. We spent a bunch of time solving for this final relationship here.
Yes.
What is the concentration of CH2CO, right, as a function of time? We then take time to infinity, get kind of that maximum final yield, okay? And then we plug that into the percent yield equation we talked about at the very beginning, right? Which is the concentration of the product you care about divided by the initial concentration of your reactant, right? If there's some stoichiometric coefficients in here, you'd have to like throw those in or things like that, right? But all the stoichiometric coefficients are 1, so.
I think he asked it before in regards to methane, that fraction would end up being like K1 over K1 plus 2.
Yep, exactly,
And
right?
you would just basically just look in and find what you want for its coefficient, and then
Yeah,
set up your basic fraction.
yeah. So yeah, and again, for methane, it would be K1 divided by K1 plus K2, okay, because methane is the product in that first reaction. Okay. And again, this will pop up again in photochemistry, because in photochemistry, you have some molecule that's excited in some excited state. And there's a bunch of different ways that excited state can decay, right? It can go back down to the ground state and emit light. It can form a different type of excited state, triplet state. It could go down to the ground state without emitting light. These different processes called intersystem crossing, internal conversion, fluorescence, phosphorescence, all these terms, right, are different types of decays of excited states, right? And then you can even throw things up even more by throwing in some molecule in your system that can take away that energy or quench the energy of the excited state. It's called do quenching experiments. And all of these things that we'll talk about when we talk about the kinetics of photochemistry are all just competing first order parallel reactions. And in the end, all the things we really care about will come down to things like this. We won't go through all the details and math and derivation that we do here, but basically saying, oh yeah, the percent yield of this thing is just the rate constant for that reaction divided by the sum of all the other rate constants. Percent yield of this thing is, so it'll just come down to the same type of answers that we get here, okay? But here we're just kind of throwing it in a little bit more detail and showing how we get those numbers, how we get that answer. Other questions about this example? All right. Let's see here. A little bit of a question, right? So I have some mountainside. I dig out a sample of ore that's 25% thorium, 234, and 75% protactinium. Okay. I know that the thorium is radioactive and decays with the given equation there to the protactinium, right? With a half-life of 7,000 or 75,400 years. Okay. I also know that the protactinium is not naturally formed in this mountainside, right? Thus, all the protactinium that you have is formed from the thorium, right? And the question is, how long ago was the thorium formed in this mountain?
Electron capture.
So, B yesterday, yeah. And the joke answer, but all right.
No, I think it's D. Yeah, two half-life.
Yeah. So yeah, so this problem, right, to solve it, you could potentially use an integrated rate law to try to solve for time, okay? But as was kind of pointed out here in class, for those online didn't necessarily hear the kind of the comments, right? The fact is, right, is your thorium has decayed, it's undergone its half-life twice to go from 100% to 50% and then 50% to 25%, okay, right? Because again, and you know that because, right, for every 1 mole of thorium that you lose, you gain 1 mole of protactinium, okay? And so that 25%, 75% ratio tells you, okay, that you've undergone 2 half-lives. And if you've undergone 2 half-lives, right, then the time it took to get there is just 2 times the half-life of this compound. Because again, it's a first-order reaction, so we can do that. If it was not first-order reaction, we couldn't do this, right? And solving this would be more complicated, okay? But since it's a first-order reaction, we could just multiply those half-lives by 2 to get D, okay? All right, 150,000 years, 150,800 years ago, right? This is when that thorium in that mountain was placed there. And again, this is the kind of idea behind carbon dating. Okay. So questions about this example? All right. So we'll just talk briefly about second order reactions, okay? Right, second order reactions, right, the rate law is just, the rate constant times A to the squared, right? Second order, that's why it has a squared, okay? Rewriting things and integrating out, you get, your final equation 1 over A is equal to KRT plus 1 over A naught, or here I subtract the A naught onto the other side, right? But right, that kind of hopefully familiar equation of 1 over the concentration equals KT plus 1 over the initial concentration, right, is the type of equation that gives you a straight line, right? So if I want to determine whether or not something is second order, right, and I have that concentration and time data, right, I would plot 1 over the concentration versus time. If that gives you a straight line, it's second order, right? If it doesn't, it's not second order. That's simple, right? And then the slope from this plot will give us what? If I plot, pulling up the equation here, 1 over A versus time, what is that slope going to equal? K, right, the rate constant. Okay. Right, so again, for first order reactions, I plot the natural log of A. For second order reactions, I want to plot the 1 over the concentration of it, right? And if you don't know what it is, you make both plots and see which one gives you a straight line, right? And then for the half-life, just plugging in for the definition of the half-life into the integrated rate law, you get that half-life expression T1 half is equal to 1 over K times the initial concentration. So note here that the initial concentration is in the half-life, okay? So the half-life depends on how much stuff you started with, right? And it's inversely related. So the more stuff you start with, the smaller the half-life is, okay? Right. And so for, again, any rate law equations, rate problems that aren't first order, right, solving for half-lives and other things like that are more difficult just because you need to know what was your initial concentration. Okay. I can't do the problem we did just a minute ago with the thorium, okay, because I can't know just what is the percent change and things like that. I need to know what is the total amount in my sample, okay, right? So you really know going to do to get the total amount of thorium in a mountainside, right? Not a really great way of estimating that because it's not going to be a homogeneous mixture in the entire mountain, right? And things like that, right? So, right. So which among the following orders of reactions has a half-life that depends on the concentration of reactant? Fifth order, first order, second order, just one of them, two of them, all three, or none of them?
Second order.
Second order does. We haven't talked about first order, or sorry, we talked about first order. We haven't talked about zeroth order. What zeroth order? It depends on the concentration. So think of a zeroth order reaction, right? So a zeroth order reaction means that the rate law is just equal to the rate constant, right? Doesn't matter what the concentration is. It's just a constant decay rate. So let me ask this. Is the half-life the same? Let's say my rate of decay is 1 mole per second. Am I going to have the same half-life if I have 1,000 moles at a decay of 1 mole per second or 10 moles at a decay of 1 mole per second? No, those half-lives will not be the same. It will take much longer to decay the 1,000 moles to 500 moles at 1 mole per second, because it'll take 500 seconds to do that. While to go from 10 moles to 5 moles, it just takes 5 seconds, right? So the half-life for a zeroth order reaction will depend on the concentration of your reactant, okay? The more reactant you have, the longer it takes, the larger the half-life, okay? Because again, the rate of that reaction is independent of concentration. So the more stuff you have, the longer it takes to get half of it to go away. Okay? Yeah, so E here, 1 and 3. Zero order and second order are both going to depend upon the concentration of the reactant. Questions? Just going to listen real quick. Okay. All right. Talk about some of these. All right. So I have a reaction A going to P that's second order in A. The rate constant is equal to, 0.25 inverse molar inverse second. How long will it take for the initial concentration of 1 molar to decrease to 0.25 molar? What do people think here? A here, Noah. So yeah, so to get this, right, we use where's it? This equation here. You plug in 0.25 for A, 1 for A naught, and 0.25 for KR, and you solve for time. And when you do that, you'll get a 12 seconds. Okay, that's how long it takes. A is the answer to this one. Okay. So again, you have a second order reaction, given the rate constant, you have some initial concentration of 0.5 molar. What is the half-life of this reaction? Yeah, so the answer is C, right? So, right, the half-life for first order, or sorry, for second order reaction is just 1 divided by the rate constant times the initial concentration. So you just take 0.5 times it by 1.33 times 10 to the minus 2, and take the reciprocal of that number, and you will get 150.4 seconds. Okay. All right. And then the final example here, I'm not going to go through, but basically you're just given data here, and the question is what's the order of the reaction, what's the rate constant, what's the half-life, right? Something you could potentially be doing in the lab, right? Where you take that data, right? In the lab, you just, make plots of this data to figure it out, okay? Here, right, I'm taking the natural log of things in order to determine if it's a first order reaction, 1 over the concentration determines the second order, okay? And then I look at the slope of these things, okay, and you'll find that it's first order based off of this having a constant slope and this having a variable slope, okay? So that's first order, so you use the slope to get the rate constant, okay? And then the half-life for first order is ln divided by the rate constant, okay? So again, I kind of brush through that, just, yeah, because of time and everything. Okay. Right. But yeah, so again, right, if we've talked about this kind of throughout class, again, this idea of if you have concentration versus time, right, to determine the order of the reaction, you want to just make different plots. You want to plot natural log concentration versus time, concentration versus time. So we didn't talk about it much, but 0th order is just concentration versus time. For 0th order reaction, A equals minus KT plus A naught. Okay, literally the equation for a straight line, right? For a 0th order reaction. Okay? And so yeah, so for 0th order, you'd plot concentration versus time, and that would give you a straight line. First order, the natural log concentration versus time would give you a straight line. Second order, 1 over the concentration versus time would give you a straight line. And then once you do that, the slope of your line is always equal to the rate constant, or at least the absolute value of that slope. Okay. And then once you have that rate constant, you can get the half-life using the appropriate half-life formula, right, that relates the rate constant and the half-life, right? The half-life is always proportional to 1 over the rate constant. It's just a question of there's a factor of ln of 2 or a factor of the initial concentration or things like that that get thrown in there, okay? but they're always proportional, inversely proportional to each other, the rate constant and the half-life, okay? All right. So kind of before we wrap up here, I'm just going to make a quick announcement. So I will not be finishing this semester with all of you. I'm going to be leaving Texas State. This was going to be my last year here at Texas State either way. But I found a position in a company and will be starting up there sometime in February. I don't know exactly when my last day is, but I'll be here until they have a replacement for me. And, I will pass them along all this stuff that I have. That person's not going to change. I would expect them not to try to change anything in the syllabus as things have been going. But depending on things, they might switch it to online only. I don't know. I'm comfortable teaching in person, but not everyone is. So that we'll have to see. But yeah, so as I said, I will not be finishing teaching this class with you guys, which I'm bummed about because I really enjoy teaching this class. I really like some of the going over to a lot of the examples in kinetics, photochemistry, and enzyme kinetics and things like that. I think are really interesting and fun examples to go over. And I really much enjoy quantum mechanics. So, and I think it's just fun, weird, cool stuff. But yeah, they're working on finding a suitable person to teach the course. And I'll be working with that person, passing them over my lecture slides and other things like that to help them out and things, so, yeah. So I'm sure whoever they have to replace me will do a very good job teaching the course as well. But yeah, so, okay. And with that, I will end the class today. If you have any questions, let me know.
Bummer.
For the new job, I'm working with a startup company that's based out of Pasadena, California, though they're completely remote right now. So I'll still be here in Texas until whenever they eventually open up an office. Probably they're saying not until September at the earliest. And so I'll be here in Texas actually, just working remotely. It's a kind of molecular discovery company. They use quantum mechanics in combination with machine learning to try to find molecules to do specific things with applications in catalysis, drug discovery, and things like that. So.
Very cool. Congrats.
Yeah, thanks. So, yeah. So again, I hate to leave in the middle, but this was going to be my last semester no matter what, and so I had to eventually find a job, right? So, yeah. So, see you guys. And if you have questions, feel free to ask.
I had a question about question 2 on the quiz, actually.
Yes.
So in your example problems on the slides, you had put it as a percent, but here you're having it as not the percent.
Oh, give us a probability distribution. Oh, you're right. Yeah, you're right. Okay. I will fix that to make it so the percentage or the non-percentage are both correct answers. Yeah, I'll do that. Do you want to email me as well? Just to, I should do it right after class, but just in case I don't, shoot me an email. It's the best way to get me there.
Yeah, I put in a percent and it said only numerical, so I put in the numerical, but I mean, it's
Yeah.
wrong, so.
Yeah. So yeah, I'll fix it. I didn't think about that. In my head, I'm just like, oh yeah, the number you get out without converting it to a percentage is this. It's just a fraction, and so I put the fraction.
That's
instead of,
why they wanted the fraction, not the
yeah.
not the
They
percentage
mean
number,
me. I'm the
not-
one who makes those answers and things like that. So yeah. So no,
Same.
that I'll fix that. That's like with those daily quizzes, I make those type of mistakes all the time. And so yeah, so I will fix that. And if if the correct answer was 30% and you put 30, you'll get full points.
Right.
So,
No worries. I had a question about the math and the half-life.
Okay.
Just specifically when we got to the ln of 2, I started to lose you. I finally hit a math wall and I couldn't think anymore. But I guess it was just the fact that like this guy was a negative, and so you're doing the.
Yeah, so
cyclical- I just
basically,
kind of lost on
yeah,
that
no, that's
little
fine.
line.
Yeah, the ln of say 1 over x is equal to negative ln of x. Or let's say the ln of y over x equals minus ln of x over y,
Sure.
or negative ln of x over y equals ln of y over x.
And in this problem, this one was already negative, so it got rid of that and just made it a positive ln of 2, because I think this
Yeah,
was like negative
yeah.
ln 1 over
Yeah,
2.
so there's negative, positive.
Yeah.
So if I just multiply that through by minus sign, right? So
Okay.
negative ln 1 over x is x.
Okay.
Yeah, that's just a property of the logarithm function, because basically
Yeah.
what you're doing is
I was just making sure that's
a
the
ln
direction.
of x is the same thing as ln of x to the a power.
Yes.
And so if a is negative 1, so it's negative 1 ln of x equals ln of x to the minus 1 power,
Minus 1, right.
which is just ln
ln
of
1
1
over
over
x.
x.
Mhm.
Yeah.
Okay, I see. Yeah, I need to brush up. Okay. Thank you.
Yep.
That was one spot I got stuck.
All right, good. All right. Question?
Yeah,